Hello guys, welcome back to my channel. Today we are going to cover week 9 and week 10 theory and some questions of MLF. So let's start. The first concept we are going to cover in week 9 is feasible direction. Feasible direction you can explain as suppose an objective function fx that we aim to minimize or maximize. We will be having an objective function to which we have to minimize or maximize, and along with the objective function there will be a constraint function. Constraint function, like, you will be given a function like gx. It can be an inequality constraint or an equality constraint. Okay. And feasible direction means the direction in which we can move from a given point while satisfying all the constraint. Okay. Suppose your constraint function is like x1 plus 2x2 is less than 9. Okay. Now you have to choose those values of x1 and x2 such that the combination should not exceed the value 9. It can either be equal to 0 or less than equal to 9, or less than equal to 9, but it should not be greater than 9. This is then feasible direction. Now there is another direction called decent direction. Decent direction means a decent direction at a point x dash is a direction in which the objective function fx decreases. Okay. As you have studied in maybe in week 7 or week 8, the gradient descent method. It was x of t plus 1 is equal to x of t minus step size times the gradient of your objective function. Now this d can be written as minus of, oh wait, this d can be written as minus step size times f dash of xt. So as you can see, these, like, if you increase the value of d, the value of this right hand side will decrease. So you have to move in such direction in which the objective function fx should decrease. This is known as descent direction. Okay, I hope it is clear. So a feasible direction is a property of a constraint function. Why it is a property of a constraint function? Because uh, the feasible direction is a direction in which you can move from a given point while satisfying all the constraints. So it is satisfying all the properties of a constraint function. That's why it is a constraint function. A direction can be called as a descent direction at a point x dash if the corresponding objective function value decreases in that direction. Okay. Which of the following condition is needed to be satisfied to decide whether the point is indeed optimal in case of constraint type? Okay. So see, for optimality condition, the point should satisfy both the constraint. What are both the constraint? The first one is inequality and second one is equality. There can be a question like you will be given a function fx. The first function is gx less than equal to 0. Second function hx is equal to 0. So if you want your objective function to be optimal, optimality should, like, if you want your function to be optimally what you can say, uh, that a point is indeed optimal in the case of constraint type, your function should satisfy both the constraint inequality and equality constraint. So the point should satisfy the inequality constraint, and no descent direction should be in feasible direction. Okay, so descent direction should not be in feasible direction. So both A and B conditions are needed to be satisfied. And a vector D is a descent direction for the function f if D transpose fx is less than equal to 0. Okay, this you have already seen here, as D is negative of your um, gradient of fx, which causes fx to decrease. Okay, now if any value x dash which satisfy constraint equation gx, then any descent direction fx will also be a feasible direction. Yeah, true. Then to minimize the objective function fx under the inequality constraint gx, which are the following necessary condition for optimality of some point x? Okay. See, mathematically, if you want to show the condition for optimality, it can be written as gradient of fx is lambda times gradient of gx. Okay. Now there are two conditions. The first one where the constraint is less than equal to 0, and second the constraint is equal to 0. Okay. So, and lambda is your Lagrange multiplier. Okay. And for minimization, your lambda should be greater than equal to 0. Now, for optimality, see, so if gx is less than equal to 0, you can substitute lambda as minus of mu. So your gradient of fx can be written as minus mu times gradient of gx. Okay. Now if your gx is less than equal to 0, this mu cannot be uh, a negative scalar, because if mu is a negative scalar, this whole right hand side will turn out to be a positive. Okay. So as you can see, the left hand side is negative of right hand side. So fx and gx should be anti-parallel, and lambda should always be a positive scalar. It should not be a negative scalar. Okay. Now when the condition comes when the gx is equal to 0, it can be parallel to each other and it can be anti-parallel to each other. Okay, and lambda can be any arbitrary scalar. Okay, I hope it is clear. Now these are our such theoretical questions. Now coming on the convex set. So convex set are the points, set of points. Like if you can show them mathematically as lambda times x1 plus 1 minus lambda times x2. If you can show these 2 points as like this expression, your points will be the set of convex set, and lambda will always be in the range of 0 to 1, including 0 and 1. So given x1 and x2, okay, x, and you can substitute this whole expression to x3. So if x3 is equal to lambda times x1 plus 1 minus lambda times x2, so this will be a convex set. And suppose you are having x1 and x2, and you need to, like, if you can substitute another variable x3 as the middle point of x1 and x2. So this is the property of a convex set, that the middle point of the 2 points, like if x1 and x2 belongs to convex set, the middle point of both the points will also be a part of convex set. So if x1 and x2 belongs to S, x3 is termed as x1 plus x2 divided by 2, is also a convex set. Okay. Now there is another property of a convex set. Suppose you are having a triangle. Okay, you can say a rectangle. Okay, you can choose any 2 points, and you can draw single line segment joining the 2 points. So if you can do this with your diagram, this diagram also belongs to convex set. Now let's suppose your graph is like this, and you choose these 2 points. Can you join a direct line segment to both the points? No, you can't. So this graph does not belongs to convex set. Same in the fourth question, a set is formed using two closed intervals -3, -1, and 1, comma 3, as shown in the picture. Is this a convex set? No, it's not, because if you choose -1 and 1, you cannot draw a single line segment joining these 2 points. So this is not a convex set. As you can see, the line segment joining any 2 points of the set S also belongs to S. Then which of the following are true about statements about the convex set? Lambda times x1 plus 1 minus lambda times x2. If you multiply x2 inside, you will see lambda x1 plus x2 minus lambda x2. So x2 plus lambda times x1 minus x2. So both are the part of convex set, and the line segment joining any 2 points of the set S also belongs to S. These are all some theoretical concepts. It won't come in end term, don't worry. Convex hull. See, convex hull you can define as mm, convex hull you can define as set of points is the smallest convex set that contains all these points. You can represent convex hull as Z summation, the value of I belonging 1 to n, lambda I xi, such that all the values of lambda should be greater than equal to 0, and summation of all, like sum of all the values of lambda should be equal to 1. So this is your convex hull. The convex hull is always a convex set? Yes, it is always true. Which of the following holds true for a convex hull? It is the intersection of convex set. Okay. Which of the following operations will result in the convex set always? Intersection of 2 points and multiplication of each element of a convex set with a fixed scalar. Epigraph. See, epigraph is another topic, such that your function is like r dimensional to r. is the set of points lying on or above the graph. The function above the graph of the function. Okay, this can be shown as P of f combination of x and z belongs to Rd plus 1 such that z is greater than equal to fx. Now, why this is not a epigraph? Because the graph is below the function. Your function is this. Okay. So as you can see, the shaded portion is below the function, so it is not a epigraph. As you can see, the shaded portion is above the epigraph, and this is only the definition. Epigraph is a set of points lying on or above the graph. So this is also above the graph, and this is also above the graph. And this is also not an epigraph because your shaded portion is lying below the graph. A function cannot be a convex function if its domain is not a convex set. Yes, it is true. Why? Because see, a convex function is represented as lambda x1 plus 1 minus lambda x2 such that your lambda is belongs like lambda belongs to the set of 0 1. See, this is the domain of your convex set. So if the domain is not a convex set, the function cannot be a convex set. The epigraph of a function is a convex set, then f is a convex function. And convex function basically uh, used for determining the local minima. And in the convex function, local minima is only equal to global minima. Okay, I hope it is clear. This is the true definition of a convex function. F of lambda x1 plus 1 minus lambda x2 is less than equal to lambda times f of x1 plus 1 minus lambda times f of x2. The linear approximation of a convex function at any point or in its domain always lower bounds of the value of the function at the point. Okay. So wait, let me find the linear transformation. The formula for linear approximation is linear approximation is f of x plus this is your step size, this is your direction points, and this is the gradient of fx. D is the direction vector. This epsilon is a small scalar step size, and this whole d transpose gradient of fx is a directional derivative. Okay, and this is the formula of you can say differentiable function of a convex if and only if x comma y belongs to real dimensional vector. Set of all global minima of a convex function forms a convex set. Yes, it is true. A convex function is set dimensional to R is said to have a global minima at a point x if gradient is 0 and there is no direction to move from x where the function value strictly decreases. Okay, see. It is saying that x1 and x2 and x1 plus x2 divided by 2 belongs to S. Then 3 by 4 x1 plus 1 by 4 x2 also belongs to S. How? See. Okay. If you put lambda is equal to 3 by 4. So see, what is the general form of convex function? It is lambda x1 plus 1 minus lambda x2, right? Where lambda belongs to 0 and 1. If you put lambda equal to 3 by 4, it will be 3 by 4 x1 plus 1 minus 3 by 4 x2. If you perform the calculation, you will see 3 by 4 x1 plus it will be 1 by 4 x2. As you can see, this is the same expression here. So it is it belongs to convex set. Which of the following is a convex function? See, the another way to find whether the function is a convex or not is d square f divided by dx square should be greater than or equal to 0. Okay. Now, if you see the first function, it is f of x is equal to ax plus b. What is df upon dx? It is nothing but a. And what is d square f divided by dx square? It is 0. So, what is the condition? D square f divided by dx square should be greater than equal to 0. Either it should be greater than 0 or it should be equal to 0. So, as it is satisfying the condition, this is a convex function. Next up is f of x is equal to e raised to the power ax. What is df by dx? It is nothing but a times e raised to the power ax. What is d square f divided by dx square? It is a square e raised to the power ax. As you can see, as you know that exponential function are always greater than or equal to 0. So it is also a convex function. Now, third expression is x square. What is df upon dx? It is 2x. And what is d square f divided by dx square? It is 2. It is greater than or equal to 0. So this is also a convex function. Now fourth expression is x cube. So df upon dx is 3x square. D square f divided by dx square is 6x. Now the second order partial derivative depends on the x and it can be negative or positive. It can be both. It depends on the value of x. So this function is not a convex function. Okay. I hope it is clear. Now what is the value of a such that this is a convex function? So your function is ax raised to the power 4 plus 8y. Find df upon dx. It is 4 4ax cube. What is d square f divided by dx square? It is 12ax square. What is df upon dy? It is 8. What is d square f divided by dy square? It is 0. Yes. And what is d square f divided by dx dy? It is also 0. Now comes the property of a Hessian matrix. Hessian matrix is df upon dx, d square f by dx square, d square f divided by dx dy, d square f divided by dy dx, and d square f divided by dy square. Determinant of a Hessian matrix is fxx, fyy minus fxy whole square is equal to 0. Okay. Now for the function to be a convex function, the second order partial derivative with respect to this should be like you can say f of xx should be greater than 0. If you do the determinant of x, you will find um, 12 ax square 0 0 0. It should be greater than 0. So if 12 ax cube is greater than 0, so a should be greater than 0. And that's the correct option, option number 1. Just remember the property of a Hessian matrix that, or you can see d square f divided by dx square should be greater than 0. What is d square f divided by dx square? It is 12 ax cube. Okay. So for this whole expression to be greater than 0, your a should be greater than 0. If it is depending on the value of a. Which of the following is a Hessian matrix corresponding to convex function? The function is a convex when the determinant is greater than equal to 0. So only this function has a determinant which is greater than equal to 0. Okay. Now, I see this is x transpose ax. This is about the definition part of week 8. So this x transpose ax is a convex function when a is a positive or a semi-positive. It should not be negative or a semi-negative. A twice differentiable function is a convex if and only if Hessian matrix is positive definite or a positive semi-definite. This is the linear approximation f of x plus epsilon d transpose gradient of fx. The function in one variable is said to be convex function if it has positive curvature or non-negative curvature. What is the relationship between the eigenvalues of a Hessian matrix of twice differentiable convex function? All the eigenvalues are non-negative. That means it should be positive. Now, oh, maybe I missed one question. Let's do it here. So the question is, a batch of cookies requires 4 cups of flour and a cake requires 7 cups of flour. What the hell is flour? It is flour. Okay. So a batch of a batch of cookies requires 4 cups of flour and a cake requires 7 cups of flour. What would be the constraint limiting the amount of cookies and cakes that can be made with 50 cups of flour? Cookies is defined as A and cakes are defined as B. So we need minimum 4 cups for cookies. That means 4A, right? And sorry, and we need 7 cups for cakes. So 7B, the 4A plus 7B, and we need max amount of flour available is 50 cups. So 4A plus 7B should not be greater than equal to 50. That means it should be less than equal to 50. So for 50 cups of flour, you can uh, find the equation where 4A plus 7B is less than equal to 50. Okay. Now, if objective function which is to be minimized, is x plus z, and the constraint equation is x square plus y square plus z square is equal to 1. The point where minimum value occurs will. Okay, let's take another page. Your function is x plus z, and your constraint is x square plus y square plus z square is equal to 1. Okay. Now first we need to find the critical points. So the method for finding the critical points are gradient of f of x comma y comma z is equal to lambda times gradient of gx comma y comma z. Okay. What is the gradient of function with respect to x? It is 1. With respect to y, it is 0. With respect to z, it is 1. Lambda times. With respect to x, 2x. With respect to y, 2y. With respect to z, 2z. Okay. You can write it as x square plus y square plus z square minus 1 is equal to 0, no matter what. So, three equations we can make from here. 2 lambda x is equal to 1, 2 lambda y is equal to 0, 2 lambda z is equal to 1. So, x is equal to z can be written as 1 by 2 lambda, right? We can write x is equal to z as 1 by 2 lambda and y is 0. Now, you have to put these points into the constraint, okay? Yes. So, x square plus y square plus z square is equal to 1. X square and z square are 1 by 2 lambda, so combining it will be 2 by 4 lambda square, and y is 0, so is equal to 1. 2 is equal to 4 lambda square. Lambda square is equal to 1 by 2, so lambda is equal to plus minus 1 by root 2, right? Now, see y is 0, right? So you can get 2 points from here. Minus 1 by root 2, 0, minus 1 by root 2, 1 by root 2, comma 0, comma 1 by root 2. Okay. So this point plots the minimum value, and this point plots the maximum value. So as you can see from here, minus 1 by root 2, 0, minus 1 by root 2 is the minimum value occurs. And for the maximum value, 1 by root 2, 0, 1 by root 2. Now 13th question, find the points on the surface y square is equal to 1 plus xz that are closest to the origin. See, origin is 0, 0, 0. Let's take a random point x, y, z. You need to find the distance of this closest point to the origin. So if you do the square of the distance, it will be x square plus y square plus z square. Okay. So this is your function. This is your objective function. And your constraint is y square minus 1 plus, y square minus 1 minus xz. Again, do the same. Gradient of f of x comma y comma z is equal to lambda times gradient of gx comma y comma z, right? So 2x can be written as minus lambda z, 2y can be written as 2 lambda y, and 2z can be represented as minus lambda x. Okay. So from here you can see that 2y is equal to 2 lambda y. 2y will be cancelled out and lambda will be equal to 1. Okay. And see, from equation 1 and from equation 3, you will get x is equal to z is equal to 0. So now your points are 0, 1, 0. Right? Um, wait. So from the you can get x is equal to z is equal to 0. And when you put this x, see, the constraint were y square minus 1 minus xz is equal to 0. Right? If x and z both are 0, this will be cancelled out. So y square minus 1 is equal to 0. So y square will be equal to 1 and y will be equal to plus minus 1. Okay. So you will get 2 points from here, 0, minus 1, 0 and 0, 1, 0. Right? So fine. So the points that is closest to the origin is 0, minus 1, 0. And for the farthest, you can select this option 0, 1, 0. The absolute minimum value of the function on the circle is, okay. See, this is your function, this is your constraint. Do the same. Gradient of fx is equal to lambda times gradient of gx. Find the critical points, find the value of lambda, put in the constraint function, you will get your minimum value as 0.47. Okay. Or should I do this? Let's do this. We have enough time. Function is given as xy square. Constraint is given as x square plus y square is equal to 1. Gradient of fx comma y is equal to lambda times gradient of gx comma y. So with respect to x, it will be y square. With respect to y, it will be 2xy. With respect to x, 2x. With respect to y, 2y. Lambda. So y square is equal to lambda 2x and 2xy is equal to 2y. Lambda 2y. 2y will be cancelled out. Lambda is equal to x. If you substitute x with lambda, it will be 2 lambda square. So y can be written as plus minus root 2 lambda. Okay. Yeah. So wait. Yeah. So see, if lambda is 0, that means x is 0, right? And if lambda is 0, that means y is also 0. So, and your constraint functions were x square plus y square is equal to 1. Put x is equal to lambda, it will be lambda square. Put y is equal to root 2 lambda, it will be 2 lambda square is equal to 1. 3 lambda square is equal to 1. So, lambda will be equal to plus minus 1 by root 3. And x is equal to lambda, that means x is equal to lambda. So, x can be 1 by root 3 or minus 1 by root 3. Y is root 2 lambda. So, y can be minus root 2 by root 3 or root 2 by root 3. So you can get 4 pairs. 1 by root 3, root 2 by root 3, 1 by root 3 minus root 2 by root 3, minus 1 by root 3, root 2 by root 3, and minus 1 by root 3, minus root 2 by root 3. And you need to find the points where the function will be minimum. So if you put these points, this and this, if you put these points onto the function, you will get your minimum value as 0.47. Okay, so B and D are the correct options. I hope it is clear. So congratulations, we have covered week 9. Now let's move on to week 10. Just give me a minute. Just give me a second, please. So we have covered week 9, right? So now we should jump on to week 10. Okay. So week 10 is nothing but another part of week 9. See, week 9 we have covered the basics of a convex function. In this week 10, we are going to cover the properties of your convex function. Okay, so let's start. So if a function is a convex, then all local minima is equal to global minima, right? And suppose you have fx and gx. Both are convex function, and the definition of a convexity is written as f of y is greater than or equal to f of x plus gradient of f of x transpose y minus x. This is convexity. So property 1 is, suppose your function f is rd to r and g is also rd to r, and both are convex function. If both are convex function, we have determined another hx is equal to f of x plus g of x. So if both f and g are the convex function, then the combination of f and g are also a convex function. This is the first property, and this is also the first question. If f and g are both the convex, then which of the following is or are always a convex function? Fx plus gx. This is the first property. You can write it as lambda times h of x1 plus lambda 1 minus lambda times h of x2. Okay. Second property is f of x is r to r, and your function is convex and non-decreasing. This is important. Your f is convex and non-decreasing function, and your g is convex function. Then h of x can be written as f of gx. Okay. You can write it as fog, and it is also a convex function. This is the second property. Let see f and g are the convex function, and h is represented as f of gx, and h is a convex function. Given these facts, what will hold true always about the function f and g? Fx and gx both are convex function, and fx is a non-decreasing function. Okay. Now, third property is your function is belonging to r raised to power d to d, and your fx is a convex function, and your g is r d to r, be linear. If fx is convex, see, if fx is convex, alpha times fx will also be convex only when alpha is greater than equal to 0. Sorry, greater than 0. Okay. Then if h is linear, w transpose x is also belongs to Rd, and see, this is a performance measure. Okay. So performance measure is sum of square error. So it is represented as minimum of w belongs to Rd, summation of value of I from 1 to n, w transpose xi minus yi whole square. Okay. This is error of xi made by wi. Okay. And specifically, goal is linear regression. So to minimize it, it is represented as 1 by 2 summation of value of I from 1 to n, w transpose xi minus yi whole square. Okay. Now if you do the derivative with respect to w, you will get x transpose x w minus x transpose y. Okay. This is a linear regression formula. And if it is equal to 0, then w can be represented as x transpose x inverse, um, x transpose x inverse, x transpose y. This is nothing but analytical form solution of coefficient w of linear regression. Okay. And the similar form for the gradient descent method for this solution is wt plus 1 is equal to wt minus step size times the gradient of wt. Okay. And this gradient of w is nothing but x transpose x w minus x transpose y. Okay. Now the function f and g, h is represented as f of gx, and h is a convex function. Given these facts, what will hold true about the function f and g? F is convex and g is a linear function. If f and g are a convex function, then h is equal to f of g can be a convex function. Why? Because the full condition was f and g both should be a convex function, uh, and f should be non-decreasing function. It is not mentioned here, so it can be a convex function and it can't be a convex function. Both the conditions can be true. If they write like f is non-decreasing also, then it will be a convex function. But for now, it can be a convex function. Fx is x square, gx is e raised to power minus x. Then f of gfx can be written as e raised to power minus x whole square, right? So e raised to power minus 2x. This is always like always greater than equal to 0. So this is a convex function. Given fx is a convex function, then minus fx is a concave. Why? Because I have already told you that if fx is a convex function, then alpha x would also be a convex function, given the condition alpha should be greater than 0. Here you can see alpha is minus 1. It is not greater than 0, so it is a concave function. Linear regression is expressed as 1 by 2 w transpose xi minus yi whole square. In linear regression, the sum of squares error is a convex function. Yes, it is true. Gradient of the sum of squares error with respect to w is x transpose xw minus x transpose y. Analytical or closed form solution is x transpose x inverse x transpose y. See, this is not for our purpose. It is not given in the lecture, so I don't know the solution of this. In the linear regression, the gradient descent approach iteratively updates the weights as wt plus 1 is equal to wt minus step size times the gradient of the function with respect to w. And what is the gradient? It is x transpose xw minus x transpose y. And all these are theory. Okay, so see, let's talk about constraint optimization. So constraint optimization, it is nothing but minimize the function fx such that your constraint is less than equal to 0. This is for the function r raised to power d to r. And Lagrange function is L of x comma lambda is equal to f of x plus lambda times h of x, where x is a vector and lambda is a scalar. So our main target is to minimize x and maximize h greater than equal to 0 L of x comma lambda. Okay, this is known as primal problem. Why? Why? Because in this, first we have to minimize x, then maximize h. If we have to first maximize h greater than equal to 0, and then minimize x, f of x plus lambda times h of x. Okay, so this will be a you can say dual problem. And there is an indicator function represented as j. Indicator function represented as j. See, if it is returning the finite value of the function f, it means if h is less than equal to 0, and otherwise it is infinity. Okay. And for weak duality functions, the value of dual optimum is less than equal to value at primal optimum. Okay. This is a weak duality, um, weak duality constraint. Okay. Now there is a theorem that is very important for weak pen. It is known as KKT conditions. Karush Kun Takar conditions. The first condition is gradient of f of x dash plus, suppose you have two constraints, the value of I to n, ui times gradient of hi x dash plus value of j from 1 to m, vj gradient of gjx is equal to 0. This is the stationarity condition. Second property is ui hi x dash is equal to 0 for all I. This is complementary slackness. Third condition is hi x dash less than equal to 0 for all I such that gh of x dash is equal to 0 for all j. This is um, primal feasibility. Then in the end, if ui is greater than equal to 0, this is dual feasibility. Okay. Now there is a small topic known as support vector machine for the optimization problem. You have to minimize w such that 1 by 2 norm of w square. Okay. This is nothing but a quadratic convex. And you have to minimize w such that w transpose xi z xi yi is greater than equal to 1 for all I. Okay. And norm of wi is nothing but summation of wi whole square. This is used for linear constraints convex. Okay. So Lagrange function is fx plus lambda times hx. If the value hx is less than equal to 0, it is hx. And if it is greater than 0, it is infinity. Your For optimization problems, you have to minimize x, then maximize h greater than equal to 0. What is true for dual problems? G of lambda is equal to minimize x such that f of x plus lambda times hx is a convex function. For dual problem, you have to first maximize h lambda greater than equal to 0, minimize x and lambda x comma L of x comma lambda. Jx is fx if hx is less than equal to 0, the equivalent Lagrangian function L of x comma lambda is less than or equal to jx for all x and lambda is greater than equal to 0 to obtain the solution for the primal problem. True. Weak duality is referred to the condition when the function value at the primal problem is equal to the function at the dual problem. False. Why? Because the value at the dual optimum should be less than equal to the value of the primal optimum. If the optimal solution holds up to some regularity condition, what is the necessary condition for strong duality? Your objective function is a convex and a constraint function is also a convex. Now, these four are the conditions for your KKT conditions. Primal feasibility is h of hi is less than equal to 0 and L of j is equal to 0. This is the first condition, complement stationarity condition. Both in an effort to satisfy KKT complementary slackless condition, which among the following statement necessarily be true? Either ui or hi should be equal to 0. Okay, this is same as this question. The equality constraint at the primal optimal solution x is greater than equal to 0. False. It is less than 0. Support vector machine is minimize w half norm of w square such that w transpose xi yi should be greater than equal to 1. The objective function of SBM optimization problem is quadratic. SBM is used for linear constraint optimization problem. True. Okay. Now these are some questions. This is the only question which you will require in the KKT conditions. Otherwise, all these questions are related to the convex function. Okay, you can do it on your own. With this video, you will be able to do all these questions. Okay. Okay. That's all. In the next video, we will cover the week 11 topics and the practice assignment of that week. Okay. Till then, goodbye and take care.